Hello everyone, my name is Alexandra Pierce. I'm in Physics 2211 at Georgia Tech, and this is Lab 2 titled Motion of a Falling Object. The purpose of this lab is to observe the motion of an object that is dropped from rest and falls somewhat slowly, straight down. I measure and analyze the observed motion using tracker. I then use Newton's second law to create two computational models, one accounting for drag and one not. I compared the observed motion to the two computational models. I obtained the result that the more forces taken into consideration, the more accurate the model. The observational model accounting for both drag and gravity was more accurate depiction of the object's actual motion. It is assumed that the only forces acting on the falling object are drag force and gravitational force, which are opposing forces. These forces do not cancel out in the beginning, which accounts for downward acceleration. There are two fundamental principles that we will be analyzing: Newton's second law and net force. Net force is equal to the sum of all the forces acting on the object. And Newton's second law states that force is equal to mass times acceleration, which means that if force is not equal to zero, then there must be some acceleration for the object. Here are some useful equations that we will be utilizing in our experiment. It's important to note that the drag force is equal to the velocity squared times the proportionality constant. Let's first look at the observed model. For this lab, I chose to drop a crumbled piece of paper. The system is a piece of paper while the surroundings are everything else. I recorded the object's motion and tracked the motion utilizing tracker, which allowed me to produce a position versus time graph for the paper. The initial conditions are listed below. Here's the video I analyzed. As you can see, I was able to produce a position versus time graph for the piece of paper. Now let's analyze the computational model with just gravity. Since the paper was dropped from rest, the initial velocity and position were set to equal 0. B, the proportionality constant for the drag force, was also set to equal 0 because this model did not account for air resistance. It only predicted motion using gravity. The net force was set to equal the gravitational force plus the drag force, but since drag force was equal to 0, F net in this code was only equal to gravitational force. Newton's second law was then used to update the position and velocity at each time step. The graph generated by the computational model differs from the observed position graph because it does not account for drag force, which is acting on the object. The discrepancies between the two graphs can be accounted for by the presence of drag force in the observed model. To make the model more accurate, the drag force should be accounted for in the net force acting on the object. As you can see, the graphs do follow similar patterns, but they begin to differentiate a lot near the end. Now for the next computational model that accounts for both gravity and drag. This model differs from the previous model because it accounts for drag force. The only thing that had to be changed in the code was B, the proportionality constant for the drag force. This value is found through trial and error. I changed the value ever so slightly each time to figure out what value would give me a graph closest to the observed motion. I found that B was equal to 0.00025. The magnitude of the drag force is also proportional to the velocity of the object squared. It is clear to see that the model accounting for both drag force and gravity shows fewer discrepancies from the observed position when compared to the gravity-only model. It can be concluded that in order to get the most accurate model, it is best to account for all the known forces acting on the object. This will ensure the model matches the observed motion as closely as possible. It is important to note that there are some sources of error present in my lab. First, I was unable to measure the exact mass of the object because I am not on a scale, so I had to do some research online to find what the mass should be. There were also some inaccuracies when capturing the object's motion at each time frame on tracker because the crumbled piece of paper was blurry in some of the time frames, so I had difficulty locating the center of the object, which can be accounted for because of the poor quality of the video. Having to predict the drag force proportionality constant through trial and error was kind of tricky because I had to base it off my observations, which had some errors in them, which could have accounted for the value being inaccurate. Terminal velocity is reached when the drag force is opposite but equal in magnitude to the gravitational force. When an object has reached its terminal velocity, the net force acting on the object is equal to 0, so the velocity remains constant. The only function that can predict terminal velocity is the computational model that accounts for both the drag force and gravitational force. However, the drag force calculated may not be accurate because the proportionality constant for the magnitude of the drag force was found through trial and error, which might not be an accurate method. What happens if the object were to be thrown downward instead of starting from rest? If the object did not start from rest, the terminal velocity would remain unaffected. The value of the terminal velocity is not affected by starting velocity. It depends only on the velocity at which the drag force would be equal in magnitude but opposite in sign to the gravitational force, which does not change when initial velocity changes. It can be concluded that terminal velocity is independent of initial velocity. Here are two examples from our computational model. One of them has a velocity of 1 in the negative y direction, and another has a velocity of 0. As you can see, they both have the same terminal velocity still.